Thank you, Nicolai. Yes, hello everyone. My name is Florent Gimbert. I'm a CNRS researcher in France, actually belonging to IGE, so not ISTER, but it's very nearby. I sit with glaciologists and hydrologists. But I do seismology mainly to understand rivers and glaciers, which I will spend most of my time talking about. Especially fluid flow in these contexts and how they affect the dynamics of these objects. I won't be talking much about the scientific questions I'm asking on rivers and glaciers, but more how we can use seismology to learn more about what's happening. And I will also talk a little bit about volcanoes, trying to convince you somewhat that potentially some of what we developed in this context also apply to volcanoes. This is work I've been doing with students and also colleagues, mostly in Grenoble, but also postdocs who now went away. So usually when we talk about water-induced or fluid-induced noise, we refer to them as tremors. And personally, I don't necessarily like this term because it can refer to a lot of things. For example, it can refer to these signals observed on volcanoes or on glaciers, where you see that the seismic energy in the spectrogram is really targeted at specific frequencies that can actually be around 4.5 hertz, as we've seen earlier. But in this case, there's much more bands that occur. And usually that's because there are resonances occurring in the conduits that generate those signals. And the resonance is usually set by the size of conduits which enter vibrations in different modes and generate those signals. This is the case on volcanoes. On glaciers, usually it happens in moulins. These are places where water from surface goes to the bottom. And you can use these signals to relate to conduit sizes, for example. But the frustrating part with these signals is that you cannot really use them to look at the water flow itself, because the signal is dominated by resonance. And if you really want to tell more about the flow of the fluid, you need to look at other signals. And that's the ones I'll be mostly talking about in this presentation. Actually, feel free to interrupt me anytime if you have questions during the presentation. So that's why I call them fluid flow-induced seismic noise. It's a bit long, but anyway. You have examples here on rivers. This one is a Himalayan river. It's the first observation that rivers can generate noise on very large scales across a range of mountains. This example is the Alpine Argentière Glacier nearby Grenoble, where you see this relatively broad frequency range having energy between 1 to 10 hertz, or even sometimes much more above. And in these cases, you can see that the resonances are not as much present, and usually they don't occur. And this is also the same in this example. This is an eruption, a paper from Phi et al. In 2017. It's the Pavlov volcano, I think, in Alaska, where you see this continuous, in this case, lower frequency signal happening. So the goal in this presentation is to, on one hand, understand the physics that sets this noise. And for that, I will go through physical models that I've been developing over the past decade. I'll start from the beginning in the idea that this is a class, but I'll try to go and move to later work at the end. And I will also talk about seismic monitoring. One of the challenges when we are interested in these signals is that sources are active everywhere at the same time. And locating sources and try to see how they change through time is actually, I think, quite a challenge. And I'll try to address some of that challenge in the second part of the talk. All right, in terms of structure, I'll start from rivers, which have the advantage of being observable at the surface. And then I'll move on to glaciers and volcanoes later on. All right, just a brief presentation of, scientifically speaking, why I'm interested in these objects. This is an example of a river in the Alps, where you see these channels all around and meandering. And I'm going to show a video which is taken from a camera nearby, on which you'll see that a flood is occurring. This is not a particularly big flood, but it's typically occurs every year. Well, it's night for half of the time, but during the flood, you see those channels that get flooded, and they shift in space. The depth of channels can change, and typically every geomorphologist who studies rivers wants to understand the interactions between turbulent fluid flow and sediment transport, and how that sets the profile of these rivers. You can see that the late profile after the flood is quite different than it was before the flood. And in fact, most of river evolution occurs during these flood events. And the main limitation of what people currently do when they study rivers is that they instrument rivers with in situ sensors, which get damaged every time there is an event like this. So this is the very big value of using seismic observations to study that, I think. Now imagine you have a glacier sitting on top of these rivers. This is really what happens in Greenland, Antarctica. The base is temperate. You have rivers everywhere below glaciers. And once it gets flooded like this, you really modify the frictional properties between the ice and the bed. And that's a very interesting problem. And that's also why I'm interested in glaciers. And in fact, I'm going to show you an example, and then I'll go through my talk. But I thought this was interesting. In fact, Zhongwen this morning talked about these interferometric radar observations that you can make. We've done that on Earth for a long time, but on glaciers, it's been particularly hard because they move fast. And so from one repeating satellite to the other, you lose the correlation in the radar signal if you want to do interferometry with it because of this 2-pi problem. And so we have overcome this problem by doing first image correlation and then do interferometry with the corrected next image. And what you see here is that there is a lake. This is a surface lake that first drains. I will show you when it does. Here, it drains to the bottom of the glacier, and right after, there's a wave propagating from here down to the outlet of the glacier. And that wave corresponds to the surface of the glacier moving faster and propagating, which is due to the water underneath changing the frictional properties and migrating at a speed, actually in this case, of about 0.1 meter per second. So it's quite slow. This whole migration occurs over 1 month, and you have about 100 kilometers of traveling. And there is big questions for people who study Greenland and Antarctica of how much these events play a role in the context of climate change. So it's not that much. In fact, if you integrate, it's 4% of the total motion for 1 year of the glacier, which is typically in those places 200 meter per year up to 500. But those events likely occur very often. And the question is how much they play a role in terms of setting the future of Greenland, because there's more melt, lakes form more and more higher up here. And this is a quite well-studied feature in Greenland. The nice thing with radar observation is that you have a line of sight observation, so you can decompose the surface velocity field into the horizontal part and the vertical part. And what you see with these observations is that they don't show the same pattern. The horizontal part is quite smooth and widespread, while the vertical part, which is the uplift of the glacier because you've put water underneath, is very localized. And you can imagine that below these areas, you have channels everywhere, which we don't know how they organize themselves, how they feed the rest of the basal interface all around. And that's what I want to study with seismology. All right, I'll skip that. All right, so to do that, we need to link what we see with the signal with the actual physics that's happening. And I'm going to talk about this first in the context of rivers. I'm going to start with a problem I've started as a postdoc at Caltech in 2014, where there was not much known about how water actually generates seismic noise. you can imagine that a lot of processes play a role. In the case of rivers, you have surface waves that we hear when we walk by. We have bubbles in the water column that can generate acoustic waves that could generate seismic waves. And you have turbulence. And because turbulence, in fact, has been widely studied in the past, I started to take this path and use what was existing to actually describe turbulence and see how much it can generate seismic waves. The physical process behind is that turbulence is you can see it as an average flow plus a fluctuating velocity component that has an amplitude that scales with the average velocity. And that has a frequency signature that is quite well defined. It's been defined by Kolmogorov in 1941. And it's set by the cascade of energy from the macroscopic shearing, so the energy that the flow is providing at the macroscopic scale by shearing, down to scales at which you can dissipate the energy by viscous friction, which is really small. And this whole cascade happens with eddies that are big and that break down into smaller eddies. And that's what sets the spectrum of velocity fluctuations and this -5/3 slope. So in fact, we can use that -5/3 slope to try to see, let's convert it into a force fluctuation and see whether we can explain the seismic signal. It turns out at the time that I didn't have the experiments, but recently, well, we have had the experiments for a while, but we have looked at them recently. It's a cobble below a channel. This is also at Caltech. And it's coupled to a force transducer, which measures the force acting on the grain at very high frequencies. And you can calculate a spectrum out of this. This is what's shown here in both for a grain that's a little bit bigger than the other. You can recognize a slope here, which is -5/3, but up to a certain frequency, the slope changes. And this is just because the turbulent eddies are not as much efficient at generating force fluctuations when they are too small. They are not coordinated each other well enough to really efficiently transmit force. This was known, so we incorporated this feature initially in the model. And in the end, what you can do is that you have this description of the ground velocity being a function of the source force and the Green's function, as we have seen before, except that in this case, we are dealing with the amplitude rather than the phase. We have seen that the force has this form. If you do the math with the expressions from empirical laws, you can show that the force has a scaling with velocity to the power 14/3. So the force is really a big function of flow velocity. And you can multiply that with the Green's function, which has this shape. In fact, it has 3 terms. There is the anelastic attenuation here, the geometrical spreading, and the factor in front of it, which converts the force into displacement, shaking displacement. Of course, if you increase the distance between the station and the river, you have more attenuation, and you turn out to have higher frequency energy. Again, feel free to ask me if you need more feeling about why this Green's function has this shape. Yeah. No, it's the ground, the seismic Green's function, which is function of the ground properties. So in fact, rho s here is the ground density, and v, this is the phase speed, and this is the group speed of a Rayleigh wave. Yeah. Yeah, so here we make the assumption that the forces are acting on each grain, which are well coupled to the ground, which in this case you can describe it as a source force. And I mean, it's a good question because there are lots of choices you can make in here. For this model, we assume that the forces acting on this grain by the turbulence are in all directions. So there are horizontal forces, vertical ones, and here I'm showing a Rayleigh wave Green's function, assuming that we don't care about the love waves because we look at the vertical component of a seismic sensor. But you could do this is the velocity at the bed in this boundary layer close to the roughness of the water. Yeah, yeah, yeah. All right, and if you multiply this by this, you get the model prediction here in green, and the observations are shown in blue. These are the ones from the Himalayas I showed earlier. So overall, you have a good shape. You also have the absolute amplitude of this. I didn't tune parameters related to flow velocity. I actually described the flow depth and the slope of the river and the real velocity. There are terms in the front here that I didn't show because otherwise it would take too much time. But that basically showed that you can explain the observations with a turbulent flow model, both in terms of frequency content and amplitude. Here, so it occurs in space. So it's always with turbulence, you have the analogy between space and frequency. In fact, a given frequency in space corresponds to a given eddy size. So this cutoff here occurs when the eddies start to be smaller than the grain size. When it's bigger, it efficiently translates all the velocity fluctuations in terms of force fluctuations. But when they start to be smaller, there are lots of them acting on the same grain, and it's way less efficient at converting velocity fluctuations to force fluctuations. And that's why the spectrum decreases much more here. Yeah. Well, this was what I showed earlier, in fact, with this cutoff. These are observations where you see this change. So when we do that, in fact, we describe this for all grain sizes. So we have a full distribution of grain sizes on which we describe the pressure on each of them, and then propagate sources from everywhere in the river to the station, and we add up all the contributions, in fact. All right. Yes, we assume that they are randomly organized. We have a distribution of particle sizes. Yeah, yeah. All right, I showed you the spectral signature and the absolute amplitude. Now I want to show you how it behaves if we change the velocity. So you've seen that there is a strong dependency on velocity. Velocity is a function of flow depth with other parameters, but here I'm simplifying so that we can go through the calculation. And flow depth is a function of discharge, the flux of water over a cross section. If you write all this and plug it into here, you get that the seismic power is almost linearly related with the amount of water that goes in a river by unit time, the volume of water by unit time. And so you can test this because people measure discharge in many rivers, and you compare seismic energy against discharge in a log-log plot. You find that the slope of this is actually quite close to what the theory predicts, which is quite satisfying in the sense that you can now back out from the seismic signal the discharge in the river. This is what we do here. Well, in fact, I reconverted in terms of flow depth here. First time I was showing this to geomorphologists, they were like, well, it's way easier to measure discharge without your model. But in fact, it turns out to not be as easy as this because rivers, they change, as I showed earlier, they change geometry all the time. The bed level is varying, and the way they measure discharge is by putting a pressure sensor in the river. And if the cross-section and the depth of the river changes, then it completely changes the discharge rating curve. So people go back in the field very often to recalibrate their pressure measurements. And you could imagine that with seismics, you can actually have a better, once it's calibrated, if you want to have a good measurement, it would be more reliable through time. And actually people now start to use seismic data to retrieve discharges. Yeah, sorry, I didn't describe these plots. this is the seismic inverted water depth, and this is the in-stream measured water depth before, we start here, before a flood with the blue dots in the early May. We follow this right scaling, so meaning with the seismic signal we can back out the right water depth up to some point where you have a big flood event here, where you have some deviation during the flood. And after the flood, you don't go back through the same scaling here. And it's because, in fact, there has been this big change in bed geometry. So there is a shift in here, just because the pressure sensor that was in the river is now under cobbles, and it's no longer exploitable. While the seismic would still give the right flow depth. That's the idea with this. Yes, I'm going to skip this. All right, so now we have seen the case of rivers, but if we move to glaciers, the big difference of channels below glaciers is that they can undergo pressurized situation. You no longer have this freely evolving surface. You are confined into a conduit, meaning that this velocity now is a function of two parameters. The size of conduits, which in this case is the hydraulic radius. It's just the ratio between the area and the perimeter of the conduit. And S is a pressure gradient, how much the pressure changes in the conduit. If the pressure change is big, the flow velocity is really fast. That's essentially what this is saying. Now you can still plug this in the theory, and you have seismic power as a function of these two parameters with some exponents. And you can do it the same with discharge, which you can also measure outside glaciers. And you can come up with these two formulations of seismic power as a function of discharge, each of them having a prefactor here, whether you change the size of conduits or the pressure of conduits. We basically replaced one parameter in each of these equations. And what it tells you is that if you imagine that the conduit is evolving at constant hydraulic radius, the link between seismic power and discharge should be really strong. While if the conduit evolves at constant pressure gradient, the link between seismic power and discharge is very weak. This is the case of an actual river, but this is a case of a pressurized conduit. And if we look at data, you actually see both scalings below glaciers. So these are observations, the points are observations on the glacier, seismic power in the y-axis, discharge in the x-axis. And you see phases where through time you follow the red scaling, which is the very strong scaling I talked about, which tells you it's pressurizing below the glacier. And you go to phases of depressurized situations, then you pressurize again, and you can have all these cycles, and eventually at the end come back to the other scaling. So this is not no longer, that's why I replicated these different scalings here. It's just a relative comparison, but you see in the data that you have these two components. And this is actually quite crucial for what I want to show later. I'm going to skip this because I feel like I still have 20 minutes or something like this. 15? Okay. I explored recently whether we can use this model to explain some of the volcanic eruptions that exist in the literature. So this is an eruption in the Pavlov volcano, on which we have people here who worked on. Matt Haney, I think, you were part of this study. What was nice is that they measured the seismic power through time, but they also measured plume height. I think it was based on videos. And they also measured the width of the conduit. So in fact, we are in a similar situation where we have conduit width varying, and what sets the plume height should be proportional to the pressure gradient you impose in the volcano. So I tested the exact same thing as for glaciers. you can write down that the height of the plume is a function of the volume per unit time. This has been documented in the past. You can plug in this Manning expression as before for the glacier. You get a relationship between the plume height and those two parameters. You can do the same between the seismic power and these two parameters. So you have two observations, seismic power and plume height, and you have two unknowns. In this case, the radius is known, but the unknown is the pressure gradient. And you can again have these two boundary scalings where if the conduit radius is varying, you have a weak but still very strong to the power 8 relationship. If the pressure is changing, you have a very strong dependency between the seismic power and the height of the plume. So I wanted to test this, and this is what's shown here. So these are data through time. The eruption lasted about 1 day. And you see that the data is really curved. So you have a strong dependency of seismic power with plume height, which we are able to reproduce relatively well with these two scalings. The red one being the varying radius scaling, and that's what we observed. The radius is changing when the eruption starts. And the green one being the varying pressure gradient scaling. Basically, once the eruption starts to decay, you probably shut down the pressure, and that causes a drastic change in the seismic power. I was happy when I saw that, but in fact, it's a bit contradictory with the work that has been done by Gestrich et al. In 2020, in which Matt is also a co-author, where they didn't look into these scalings here, but they rather tried to explain the absolute seismic power generated by the volcano. In both cases, whether you use this turbulence model that I've shown you before, or whether you assume that noise is created by impact, so grain impacts in the volcano, with the typical values we think of, it's way below what you observe. But you can push these models by saying, well, maybe there are big grains in the conduit that we don't see at the surface that exist, and maybe that could explain the observations. I think that was the claim in the paper. The turbulence, it's hard to make it fit because the densities that you would need to capture the observations are really somewhat unrealistically big. In the end, I don't know what really explains the observations, but I think we will need to do further work in terms of developing more accurate models and maybe compare with more observations. If there are questions on the volcano, then I'll skip to the second part. Yeah. This one is from seismic. Yeah, they had both. They had acoustic and seismic, but this one is seismic. Yeah. It's just one. Yeah. 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 All right. So just to summarize on this, I'm longer than expected. Yeah, turbulent fluid flow is a good candidate to explain noise from rivers and glaciers, and it's a potentially good candidate for volcanic eruptions. Also, more work is needed. And potentially we can use this to actually study rivers, discharge, pressure in conduits, and things like this. And I will get back to this at the very end if hopefully I have time. I'll try to go a bit faster on this component. But I told you I want to locate sources around rivers. And for that, we deployed an array that looks like this. It's a bunch of subarrays all around the river. And the goal is to locate sources. This is the work of Samida, who started a PhD with me not long ago, so it's preliminary work. And we focus on a big flood like this, similar to what we observed I showed you initially. And the constraint we had to try to locate the sources is that we sample the wave field at a sub-wavelength scale so that we can do beamforming. And we deploy arrays densely enough with respect to each other so that we can hope to locate sources by merging match field processing for the different subarrays. It's a bit of a compromise between sampling the wave field at the subwavelength scale and trying to locate at the relevant reach scale of the river. Because typically what the beamforming or match field processing tells you is that you expect, with a given subarray like this, you expect to locate sources if their distance from the subarray is smaller than 2 to 3 times the aperture of the array. And that's the circles you see here. This is 2 to 3 times, this is 3 times actually the aperture of the array. So potentially we can locate sources within this area with this array, but for sure we will be quite bad if we go too far. And the idea is to have another array that takes over and maybe try to make the localization better. So I wouldn't be able to tell you exactly where it comes from. Well, it comes from this paper. Yeah, I don't know to which the extent to which it's actually theoretical or empirical, but yeah. That's right. That's right. Yeah. Yeah, yeah, yeah. Yeah. It's the limit when you go from a plane wave to a circular wave situation. All right, and the signals we see look like this with the different subarrays. So you see that there's coherency across, I mean, within one array, but across arrays there's phase steps, and that's why we need to work array by array. And that's what we do. We do the regular match field processing technique, which I'm going to skip the description. If you do it by array, you find that the MFP output exhibits a maximum into some direction. In this case, you cannot really pinpoint a point. In this case, you can. It would be the blue star. You can, but it's really blur, right? It's not very well defined. But what we try is that we do this and then stack all the match field outputs in space together. That's what's done here using a uniform velocity varying from 50 meters per second to 490. You see that at low velocities you have a quite bad map, and then it gets a bit better and you can potentially locate events in this case. If you look at the maximum MFP output, so the phase agreement between predictions and observation here, across the different phase velocities, you find that you can use an optimized velocity here, which would lead to a map like this. So you can guess where the source is, but it's not very precise. Then what we tried is to now optimize the velocity by subarray and again stack the field all together. So by subarray, you will see that the velocity is changing just because the ground velocity around the river is changing. And then we stack again all the fields together, which is a bit weird conceptually, because that means that at a given point, for this array, we will use a given velocity. For this array, we will use another one. But in the end, it's a way to optimize the phase velocities within each array so that we match better the field. And it turns out that you get a better solution. The shape here is more resolved. And you can even pinpoint other secondary sources like this. No, we didn't. In this case, it's uniform by array, by subarray. But we would need to move to that, I think. Anyway, if you do the exercise here, you have a velocity by array, and you could do that systematically in time and find a bunch of points here which potentially are real sources. If you pinpoint the maxima here and you show them in a map, this is the map you would get over 30 events on the left, with the uniform velocity and the one here with the optimized velocity biarray, where you potentially can start to see the river, although we need to work more on this. This work was actually inspired from what we had done on glaciers before, which is what I wanted to briefly show here, except that on glacier, we use this array here, which is at the glacier surface, and we did that systematically through 1 month of records. And instead of doing the grid search, as I showed before, we did the minimum gradient algorithm, actually developed by Alban Lecointe, who is in the room. I don't know where, but oh yeah. Where we start from a given point and we go find the local maxima in the MFP output between the model and the observed phase. We keep all the local maxima and then make maps with it. Of course, if you take the high beam values, you find that you can locate crevasses, such as, for example, this one. Although the focal spot is much bigger than sources that you see, you can see that the sources from one time to another really align along a crevasse area, although the focal spot is much bigger, which leads us to think that we are highly resolved in terms of location in this case, but these are for high MFP outputs. Actually, you can go check Tiffaine Lebris' poster, where she also does some beam forming in Antarctica, and she's here. And you can, of course, this is just for fun, these are crevasse events that you can locate very well with this technique. You see events varying through time, and sometimes you see migrations like this, where crevasses go from one place to another. And this happens all the time. You have another crevasse here, another one here, and here. But basically, this is when you look only with the high MFP output values, so we would be in this case here. But when you go to look at lower MFP output values, you can go down to cases where you see those stripes here, or where you see this shape here. We think those are scatterers from the cobbles at the surface of glacier. We can see those stripes here. So these are probably not active crevasses. They are reminiscent crevasses that trap cobbles in them and make scatterers like this. And we think this is the subglacial flow that we are able to locate. And we can look at how it varies through time. Over the season, you can see that the map of the subglacial hydrology sources is quite widespread at the beginning, and then it gets more narrow and narrow, which is somewhat consistent with what glaciologists expect, where you first have at the beginning of the season quite widespread hydrology below glaciers, and then it funnels into rivers. So this is work that we have published in recent papers. And yeah, to finish on this, so this is the intermediate conclusion about how we can locate all these varying sources in space by doing match field processing is one way of doing it. I know other people do it with looking at eigenvectors and doing PCA analysis. And the other conclusion is that we can look at the spatial and temporal dynamics on both rivers and glaciers. Also on the river aspect, we need to do more work. And I just wanted to finish with this slide showing the future work we are planning to do in the context of an ERC project that I've been having recently. So over the next 5 years, we will go study Greenland by deploying seismic sensors into arrays like this, do DAS monitoring both at the surface and in boreholes, and try to look at imaging the subglacial hydrology sources and also maps of water storage in isolated pockets like this, which we think are quite ubiquitous below these glaciers. And I thank you for your attention.